Today we're going to start talking about combinations. A combination is just like a string, only the order of the elements doesn't matter. When we talk about a combination, the length of a combination is just the number of letters it contains. I like to think of a combination as like a bag of balls with numbers on them or letters on them. Instead of writing a string, say A, B, B, C, think of a bag with 5 balls, 2 A's, 2 B's, and 1 C. That makes it clear in your mind that the order doesn't matter. Here's an example. From the standard English alphabet, you can talk about a combination A, B, C, D. That's a 4-letter combination. If I just say the combination B, A, C, D, that's just the same combination. It's the same 4 letters. When we're talking about a combination, their order makes no difference. So when you write down something like A, B, C, D, you should be clear if you're talking about that as a string, in which case the order does make a difference, or if you're talking about it as a combination, in which case the order does not matter. Here's another example. This combination A, B, 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 C, C is the same combination that you might write as B, A, B, C, B, C. In both cases, we have 1 A, 3 B's, and 2 C's. This other combination, A, B, B, C, 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 is a different combination because this one has only 2 B's and 3 C's. That's different from the previous one. Here's our first important question. Well, a first question that we've already talked about in class. How many combinations are there of length 2 from the alphabet A, B, C, D, E? That's a 5-letter alphabet, if we do not allow any repeated letters. And let me say at first, we're going to be talking a lot about different types of combinations. Very frequently, we'll be interested in combinations that have no repeated letters. Later, we will talk about combinations with repeated letters. So in this case, we want to talk about how many combinations there are of length 2. Well, I claim we've already kind of solved this problem in a different form. What is a combination of length 2? What are the examples? Well, I'll just write down some. AB is a combination of length 2. AC, AD. In fact, let's try to write all of them down. AE. These are all the combinations of length 2 from this 5-letter alphabet that contain no repeated letters, which include an A. If you include an A, then you could have, along with it, a B, C, D, or E. If you don't include an A, let's say you have a B, we already have BA, which is the same as AB, so we could have BC, BD, and BE. Every combination that has either an A or a B is listed here. Well, what if there are no A's or B's? Well, we might have a C. We already have the CA and the CB there, so we could have CD and CE. I claim now we've got all the combinations that have any A's, excuse me, B's, or C's. And then what else is left? Well, we could have the combination with no A's, B's, or C's. That's just DE, and that's the only one. So how many do we have total? You can count them up, and there are 10 combinations of length 2 from this 5-letter set. We can talk about this number 10, the number of combinations of length 2 from this 5-letter set, as being the same as the number of ways 5 people together in a room can shake hands. We talk about a handshake between any 2 people. So imagine we have the people A, B, C, D, and E. Let's say those are their names. Each of these 2-letter combinations represents a handshake between the 2 people, and there are 10 ways that can happen. Another way to think about it is, how many ways could you position, say, 2 X's in these 5 spaces? You could put them here and here, here and here, anywhere else. If you think of this first space as representing space A, second for space B, third for space C, D, and E, like that, there's this one-to-one correspondence between placements of 2 X's and combinations of length 2 that we've written here on the right. This placement of the 2 X's would correspond to the combination BC, Wherever you place the two x's, just look at the combination that contains those two letters. And this idea that there's this one-to-one correspondence between ways to place two x's in these 5 spaces and combinations of length 2 from this 5-letter alphabet tells us they have the same size. We're counting the same things. We're going to get 10 as the answer to all of these questions. So now we ask the important question, can we generalize this? Well, we ask the question, how many combinations are there of length 2 from a 5-letter alphabet? Can we answer the question, how many combinations are there of length 2 from an n-letter alphabet, if we do not allow any repeated letters? So instead of a 5-letter alphabet, we might have a 7-letter alphabet, or a 12-letter alphabet, or a 122-letter alphabet, any number n. Well, can we answer it the same way? We can't just list them all if n is large. But we have several ways we can approach this problem. We know how to answer a different question. How many 2-letter strings are there? So now I'm talking about strings where the order matters. From an n-letter alphabet where we have no repeated letters. I'll just write no repetitions. And this is a question we've already answered. We can just use the product rule and construct here a 2-letter string can be constructed by choosing a first letter and a second letter. We have n choices for the first letter, since we have an n-letter alphabet. And since no repetitions are allowed, we only have n-1 choices for the second letter. We can't use the same letter. The product rule then tells us there are n times n-1 2-letter strings with no repetitions. This is like standard problem number 2. Now, how does that help us answer how many combinations there are? Because remember, in combinations, the order doesn't matter. Well, anytime we have 2 letters, let's say 2 of the letters are A and B, we would be counting AB and BA as different strings. But if we ignore order, they represent the same combination. I claim that among all of these n times n-1 2-letter strings, we can pair them up. For each string, just reverse the order of the letters and call that its pair. Think of that as a pair. And we can divide this into many different pairs. Well, how many different pairs are there? There will be n times n-1 divided by 2 pairs of strings, each one of which just consists of 2 letters in one order and then the other order. Each of those pairs will represent a single combination if we now ignore the order. So this is the number of combinations. Remember, that's 2-letter combinations from an n-letter alphabet with no repetitions allowed. Can we generalize this even more? What if I want to talk about combinations of length k from an n-letter alphabet? Before we had just combinations of length 2 from an n-letter alphabet. Now I want to allow combinations of any length k from an n-letter alphabet if we do not allow any repeated letters. Notice right away, k cannot be bigger than n, because if you don't allow any repetitions and you only have an n-letter alphabet, you can't have more than an n-letter combination. Well, we're going to do the same thing as before. From standard problem number 2, we know that the number of strings of length k from the n-letter alphabet, I won't write that down again, with no repeated elements, no repetitions. We know that that answer is just n times n-1 times n-2 all the way through n minus k plus 1. We have k different letters to pick, n choices for the first one, n-1 for the second, n-2 for the third, all the way down to n minus k plus 1 for the kth choice. Now, anytime we pick a string of length k, there will be k factorial rearrangements of this string, because we have a string with k distinct elements. So group all of these n times n minus 1 times n minus 2 up to n minus k plus 1 strings into groups of size k factorial, where that group consists of a string with all of its rearrangements. And each of these groups will represent just a single combination because they contain the same letters, just with different orders. So since each of those groups represents just a single combination, the total number of combinations is then n times n minus 1 times n minus 2 up to n minus k plus 1 all over k factorial. And this is our really important formula that tells us how many combinations there are of length k from an n-letter alphabet when repetitions are not allowed. This is the result in standard problem number 3. Find the number of combinations of length k that consist of distinct elements from a set of size n. The answer here is what we wrote down before, but there are other ways to write it. For example, that numerator here, n times n minus 1 times n minus 2 up to n minus k plus 1, can be written as n factorial over n minus k factorial, because n factorial is n times n minus 1 times n minus 2 all the way up to, going all the way down to 3 times 2 times 1. And if we divide by n minus k factorial, that's n minus k minus 1, all the way down to 3 times 2 times 1. We're just canceling everything after, everything that would go here if we continued with the n minus k minus 1, etc. In other words, think of this divided by itself. The numerator would be n factorial now, and in the denominator we have the k factorial times here's n minus k factorial. So this is a simple form involving factorials to represent the number of combinations of length k with distinct elements from a set of size n. This is such an important quantity that we have several different names for it in combinatorics. We can write it as nk like this with the parentheses. We can think of that as a binomial coefficient, nk, or we'll usually say it as n choose k. Sometimes we'll use the notation cnk for the combination number nk. Some books use nck like this. Our book doesn't use that one, so we'll tend to avoid it, but it would still mean n choose k, or the combination number nk, or sometimes we'll call it a binomial coefficient nk. We'll learn more about why we use those names shortly. Two quick examples. How many ways can I pick a group consisting of 3 students from a class of 30 students to work on a group project? So I've got a class of 30 students. I just need 3 students to pick to work together. Well, I need to pick a combination of length 3. What matters is which students there are, and it has to be a combination with no repetitions. I'm not going to say I need 3 students, so Bill, I'm going to take 2 of you and 1 of Alice. No, you can't do that. You have to pick 3 distinct students from the 30 students. So the answer, I'll write down as 30 choose 3. If we need to know the exact numerical value, we can use the formula. That's 30 times 29 times 28 over 3 factorial, which is 3 times 2 times 1. You could write this as 30 factorial over 3 factorial times 27 factorial if you want. If you're just computing it by hand, even though this might look like a beautiful formula, which it is, these are big numbers, 30 factorial and 27 factorial, and they, in this case, mostly cancel out, so it's often better to use this form. Which form is nicer depends on what you want to do with it. If you want to write down the answer on a quiz, either form is just fine. And of course, if you pick up a calculator, maybe your calculator can compute these combination numbers directly. If it can't, it's probably easier to have it do this. Or many calculators nowadays can do this. When I was younger and the calculators were simpler, a number like this would give you an error message because those numbers would be too big for the calculator to handle. Here's a related question. Let's say I have 30 students in a club, and we need to pick a president, a vice president, and a treasurer. So I need to pick 3 of the students. But notice that now these 3 students will get specific jobs, president, vice president, and treasurer for the club. How many ways can I pick them? Or can they pick them? Well, the answer will be different from the answer to the previous question. Why? Because this is now like picking a string. Of length 3 with distinct elements from the class of 30 students. So we, just like we've done before, we have 30 ways to pick the president. We now have only 29 ways to pick a vice president, and we have 28 ways to pick the treasurer. Or you can do this in any order you want. In the end, you'll have 30 times 29 times 28, whatever that is.